Okay, now let's take a look at verification plans. This is where we specify how you go about verifying that the requirement is met. So we're specifying, making a claim that in order to meet the requirement, here are the set of things that I'm going to do, and I'm trying to convince you that that is sufficient evidence for you to accept my assurance case. So there are several pieces to that. There's a method registry, and I'll talk about that in a second. This is where you define reusable methods that can be implemented in a variety of things like Java, Resolute, or Python, or make use of existing OSATE plugins. And we can characterize those methods, categorize them for filtering, the same way we can categorize requirements. Verification plans. This is where you specify the claim for each of the requirements, and in the claim list out the verification activities, namely the invocation of a verification methods on certain artifacts in a model or artifacts associated with a model, for example, on code that implements a particular component in the ADL. And in that context, you can make some arguments about which combination of verifications have to be satisfied, or if one fails, whether there's a backup and those kinds of things, or preconditions and validation of verification results. And in an ELISA part of the notation, we can then compose those plans into assurance cases that can be executed. So when we look at verification plans, we have a requirement, R3, that talks about some voltage for an incoming feature called power. We have a constant in volts with a unit of volt. We have a compute variable. Compute variable is like an unbound variable for a lambda expression, and the lambda expression itself would be what's the value predicate. So what we see there is we have volts, which is the constant, which is the expected value, and the compute variable will contain the value that comes back from a verification activity. The idea here is that we have a predicate that is specified once in the requirement and is applied to every verification activity. Another way of doing it is that the verification method itself has in its code implemented this particular predicate. It's often the case that you do that. The issue, though, is if you have written 5 different ways of verifying the same thing, you need to make sure that the predicate is correctly specified in all 5 of those implementations. Whether you compare less than 50 or less and equal to 50 or change the value, those kinds of things need to be done consistently. By pulling the predicate into the requirement, we have effectively a shared predicate that gets automatically applied. So this is what we are showing here. In the verification plan, you write a verification plan against a requirement set. Within the verification plan, you write a claim for each requirement in the requirement set, system requirement set. So claim R3 is basically R3 is a reference to the requirement. You list out a set of activities. The first one is the invocation of a verification method that, as parameter is passed volts, it itself will then execute some values and do the comparison, so it acts as the predicate and return true or false. The second one illustrates the invocation of a verification method that's basically a compute method. It does some computation, returns a value. That value then gets assigned to the compute variable, and we then invoke the value predicate. And then the result of the value predicate determines whether this activity is satisfied or not. And the third one is an example where we are indicating we are invoking a method, and in that method it makes use of property values. By specifying that, we then indicate either if the property has already assigned value in the model, that it is the same as the one specified by the constant volts, or if it's not specified, we then automatically assign that value into the property on the model so that the execution can make use of the property value. In the bottom, we have an example of a verification activity for the claim of latency that makes use of some argument logic. What we have is actually two activities. One is doing some scheduling analysis, and the second one does flow latency analysis. We then write down as an assertion that the response time, the latency analysis, can only be done once the timing analysis has been performed, because the latency analysis lives off the assumption that all the deadlines have been met, that the system is schedulable. So that is recorded as part of the logic here. Again, something that the first part is something that I already said, that is, we have the compute variable, like a free variable in a lambda expression. It can be typed in terms of types. We can make use of types that are defined as part of the property language. Then we have property types. We assign the result value to the compute variable, and then the bottom we are showing how you characterize the verification method. We are indicating a method that applies to features like ports and so on, and in this case takes a parameter. In the second case, we have a method that again takes a feature and returns a particular value, and it's this latter one that then lets you assign the return value to compute variables. In the registry itself, we then have some text that describes the method, and we identify a path to, in this case, for a Java method that is in some Java class defined in a project called Elisa Consistency. When we write down verification activities, by default, all verification activities are executed. All of them are always executed, so you might have an activity where the first one fails. It does not stop the verification activity. All of them are executed, and then the result is that the claim is only satisfied if all of them are return success. That's different from you using AND OR logic, where you say traditional logical AND, which typically has a shortcut. That is, if the first one fails, you don't bother evaluating the latter operands. This was an early implementation of Resolute that did that shortcut, and later on, based on the work we have done, they improved the way they were doing the AND as well. And similarly, they had the ability to specify an OR. What does OR really mean? Does it mean you can arbitrarily choose one or the other? And the third operator that they had was an implies, but that often had unintended consequences, because implies means if the first one is false, then the whole implies is true, which is in most cases not what you wanted. What we have done is basically said, okay, what is the logic that we really want? We want the logic of all, which is an AND without shortcut, that all of them are evaluated, and in terms of logic, they all have to be true for the claim to be true. The second thing that you want is conditional. That is, if the first one is successful, then you perform the second one, otherwise you don't, and both. And then the third one is that it's conditional in the sense of, if the first one fails, you want the ability to execute an alternative. One example of that is if you have, say, a long-running proof verification, with a timeout, and it happens to not come back with the result in half an hour, which was your timeout condition, then you might switch to a second verification activity that is much shorter running but doesn't give you quite as much confidence. And for that second one, we can then elaborate whether the fail is because of timeout or because of an other execution error. You might have a verification activity that just crashes, and so you want to be able to specify backup activities. In terms of a registry of verification methods, the idea behind it is that we have a uniform signature definition for verification methods that are being invoked in verification plans, so that while you write the plans, you don't have to know whether this thing is implemented in Resolute or Java and what form it takes its parameters. There's a single interface, and the registry itself provides the information for appropriate mapping. We support the invocation of analysis plugins the way they are, invocation of Java methods, including existing analyses that are also available as plugins. Some of those have been now exposed as Java methods, where you can invoke them that way, and you can write Java methods and make them available through a plugin, or even just have them sit in the workspace in which the ADL models are that need to be verified. We just recently added the ability to write Python scripts to be executed. We support the execution of Resolute claim functions. We had a prototype interface to agree as well. That needs to be updated. And we had a prototype interface to JUnit-based execution of Java classes that then themselves can execute whatever they want, whether it's the source code that goes in or via this Java interface. You execute other things like C code or whatever else you want to invoke. Here's an example of a Java-based specification of verification methods. The first one. So in all cases, you map the method to a method in a Java class. So you just specify a path for it, and you specify parameters that are expected. You indicate which model element it applies to, whether it's a component, a feature, a flow, or a connection, and additional parameters. As I mentioned earlier, some of them are where the method itself determines whether certain things are satisfied, true or false. So we can return true or false, and we deal with that accordingly. Methods can also return individual values, and like the second one shows, that then can be assigned to compute values. There's also a generic representation for analysis results that we have defined as part of USAT. It can contain multiple results, like a collection of end-to-end flows, or in the case of an end-to-end flow, multiple data elements, and how the computation is achieved by various sub-results. In that case, then the data that is part of that result representation can be mapped into those compute variables. And we'll see an example of that. And we have a way of specifying the property values either for setting them or for making sure they're consistent. When writing Java methods or Python methods, you have access to libraries of classes that are available within OSATI, the same way that you make use of those when you write a plugin, and then the help will point to you of 5 classes that are the most important ones. You do that by having a plugin dependency into OSATI. A second way that we just recently added of making available access to Java classes and methods is an extension point that then is interpreted. So that allows you to bring in analyses that are through additional plugins like the fast stuff from Adventium, or Java classes that are written without necessarily relying on the plugin mechanism, especially if you also want to exercise JUnit type of tests, either as part of Alisa or independent of Alisa. You may want to start making use of this extension point mechanism, and that is coming out with the next release and is currently available in the testing version. The verification methods are an example of the plugin. Is, well, there is all you do is name the plugin and we figure out how to find the plugin. In the case of Resolute, it's similar to the Java one, except you're identifying a Resolute claim function, and you do that by specifying a full path with the package name, the public section of the Resolute, and then pointing into the Resolute Annex library, and with the .resolute, and finally the name of the claim function. In the case of Python, it's similar. You have a Python script sitting in your workspace, and you identified the project appropriate folds and then the name of the file without the extension, and we then make it available for execution. So what does that look like in terms of our example? Let's first take a look at verification plans for SCS. So here we have a claim for the requirement R1. It's hyperlinked, so we can get back to the requirement. And by the way, there's a quick fix if you are missing claims for requirements. We tell you which ones are missing and can autofill those in. You then just write your requirements. In terms of activities, in case of weight, I'm making use of the mass analysis that's defined via plugin mechanism. I also verify it through an implementation of a mass weight analysis written in Resolute. And a third one that has higher level verification activity, in the one case we just invoke a Resolute method that recursively does the summing up. And the other one was written where we first emulated the structure of an assurance case purely within a Resolute, where you define even requirements as claim functions and do those recursively here. And then you perform various things on it. In the case of claim R3, we are invoking a method that gets the voltage, assign it here, and then we execute the predicate associated with R3, which is what we saw in the slides before. And we also have the invocation of a method that happens to be implemented in Java, and we'll see that in a moment here. So in the case of Resolute, there are some basic Resolute compute functions and claim functions that we use for various purposes. The examples here are about connectivity, are all the ports connected and those kinds of things. And then the second one is a re-implementation of the functionality of the weight analysis within the Resolute. And this one was done in such a way that the top level is written as a requirement for both DCS and SCS, so that you could insert those as proof statements into the ADL model. This is what you would have to do with Resolute, is write your Resolute, apply a proof statement to the top level. You made first claim function either reflects the requirement or finds all the elements for which we want to apply a requirement and the verification activity that actually does the verification. When you do the same thing in ELISA, you just focus on the claim function that does the actual evaluation. ELISA takes care of finding all the instances of objects for which it applies, and also takes care of relating the verification activity to the requirement. So those kinds of things you don't have to do in Resolute anymore. That's taken care of on our side. And you don't have to pollute your ADL model with proof statements. When you want to write certain things in Java, you can do that as well. So here's an example where we have written a couple of Java methods. Again, the connectivity are all features connect. So here's, is it connected? I pass in a feature instance and I say, is this feature connected? So now on the ELISA side, I can have a possibly even a global requirement that says for all features, I want to make sure that they are connected. And then ELISA takes care of applying that verification to all features in our model. Or you can do it targeted for specific ones. You can also write a method that does it for a whole component. And in this case, I'm illustrating how we make use of the result mechanism, this generic result reporting capability that comes with OSATE. So I want to return a result for this verification activity. And the idea behind the result is to report back whether the result is successful or not. And if it's not successful, have a record of things when something went wrong, namely a feature was not connected. So what we do here is we look at the features. And if the feature is not connected, leave a diagnostic message as part of the result. And then on the other side, when we have executed the verification activity, we then determine whether the verification activity has passed or failed, depending on whether we find diagnostic failure issues in the result. And we have an example of JUnit where we have the Java code here, and we have a registry that makes that available for execution. Back to the presentation. One of the things we have is the ability to categorize requirements and verification activities. The idea behind it is we can do filtering, and we can, for example, specify development phases. So if you walk into a PDR or CDR, we can now produce an assurance case specific for what's expected for a PDR or CDR. Or we can have filtering in the sense of dealing with just weights or dealing with just performance and security. We have a predefined set of these things, various quality attributes that we are interested in, various development phases, system layers, and if you want to characterize whether it's assumption or guarantee, or characterize the requirement itself, is it a consistency, is it a constraint, is it an exception that we are dealing with, you can do that, and you as a user can define additional categories. And we then just make use of those in the model. And we saw some examples before where we categorized the requirement, but you can also categorize the methods themselves. And before I go back to the demo, let's just touch on what an assurance plan and assurance case looks like. An assurance plan is now the specification of a set of verification, which verification plan make up the verification of the system, which model instances are included, how much of the system is verified, whether subsystems are verified or not. And then we can instantiate that assurance plan and execute it, and can do that based on filtering. So what does that look like? We are defining an assurance case for a system. Within an assurance case, we can have multiple assurance plans. Each assurance plan identifies a route for an ADL instance model. So different assurance plan can basically verify at different levels of fidelity. So a tier 1 verification, tier 2 verification, and so on. And then within the plan, we identify the verification plans, or they can be auto-filled in, all the verification plans that have been defined for this particular system. We can configure in global, reusable requirements and verification plans. And we can identify which subsystems should be verified as well, and which subsystems do we assume have been pre-verified, so that we are not responsible for verifying them. We can also define filters. Filters are nothing else than a list of categories that make up that filter. We can define that as part of an assurance case. It's called assurance task, or we can define it as a filter in the same files that you define your categories, and that there they become reusable. When you do this whole thing, and I'm now using as an example the multi-tier aircraft models, we have requirements and verification plans for components at different levels of your architecture, different tiers. And once we configure those all together, we now can define an assurance case with plans for a tier 1 verification, tier 2, and tier 0, 1, 2. We can also define assurance cases just for a particular subsystem, and then we do the focused verification. The multi-tier aircraft model has all kinds of things in there, so this was to show how complex a verification we can represent and automate. This is from the Savvy initiative. The one that, for the simple example, is shown here now. You get to it by opening a view, an assurance view. You go under Window, Show View, ELISA, it comes up. On the left-hand side, it fills in all the assurance cases that are available, appropriate filters. By default, we show everything, and if filters are defined, you can select which filter you have. Once you have the system, you right-click in the context menu and then invoke the verification, which then creates an instance of an assurance case, and then it starts executing it. And what we see on the right-hand side right now is the result of the execution, which has a number of passes, a number of fails, and a number of executions that fail to execute. You can then open up and drill down to find where you have your passes and failures, and it goes all the way down to claims, various forms of evidence, and in the case of positive or negative evidence, and there is more detailed results, you can find out the details of that. That is, for example, in the case of Resolute, when there are nested claim functions, the substructures are shown here. If you do a latency analysis for an end-to-end flow and you have the latency contributors, they become visible in here as well, the same way that they are displayed in a latency report. And given all of that, you can move towards basically a metrics-driven execution of these things. This is where we need have a potential often have dashboard type of things that show you a history of the metrics, requirement coverage metrics. There's a view, a prototype of a view that shows you how well we cover requirements. You can add some weighting and activities like that to drive that forward once we have the basics in place. So what does that look like in ELISA? We have our example assurance case for the system. It's basically the one shown on the slide, and again all of this stuff is hyperlinked. So we have our assurance case I right click, I say verify all. It then just goes through and executes everything. You can watch live as to how it does it. It updates as these things are executing. In the underlying representation, there's even a record of how much time is spent on each verification activity, so you can get a sense of that. If you now want to change to see a subset of this thing, I can change the filter, and then you would see a subset of that. The version that I'm running right now is Osati 235. It had a problem with switching filters in the testing release, and the next release 236 it will switch it accordingly, and I have that version available to make you see that as well.